All right. Good afternoon, everyone, and thank you guys for being here. Welcome to our August 2026 installment of ENERCALC Office Hours. You guys who have been with us before know the drill. We have just a few quick housekeeping items to blast through before we begin today's program. So, before we get going, I'm going to just start us off with a quick sound check. If you direct your attention to the bottom menu of the Zoom window in your browser or your desktop app, you'll see that we have the chat tool. We also have our reaction emojis down there. If you can give us an OK in the chat, give us a thumbs up, an applause reaction, your emoji of choice, then we'll make sure that you can hear me just fine. Perfect. Thank you guys so much. You guys know the drill. You're pretty good at this. Thanks for confirming that. Before we get on to the rest of our stuff today, we're going to also do a sound check and visual check for our primary speaker. So Mac is going to go ahead and share his screen right now. And once again, if you can hear Mac's voice and see his screen here in a moment, then go ahead and give us a reaction once again. Go ahead, Mac.
Hello, everyone, and welcome to another great office hour session.
Fantastic. Thank you guys for your help in our tech checks. We always appreciate that. Now that we have that out of the way, we are going to go ahead and disable the chat, and then we'll move on to some introductions and get going with today's program. So my name is Seth Roseworm. I'm a senior structural engineer and software developer here at ENERCALC, and our presenter for the monthly ENERCALC office hours program is Mac Elterhony. Mac is a senior structural engineer here at ENERCALC, and he splits his time between providing technical training for ENERCALC customers and working with the engineering team here at ENERCALC on specifications and technical behavior of our software, as well as helping maintain a presence for ENERCALC at national and regional events throughout the structural engineering industry. A lot of you also may have crossed paths with Mac professionally, as he is the founder and managing principal of Elta Design Group, which is a specialty structural engineering firm based in Dallas, Texas. And Mac's been an ENERCALC user for over a decade, so he has a lot of great insight about the needs of our customers. For anybody who's new here this month, Office Hours is all about providing lines of communication between you guys, our users, and the ENERCALC engineering team. And we do that through several avenues. We showcase new features and the latest, greatest updates to let you know what's going on in the ENERCALC program as we roll out updates month over month. We show optimized design workflows where we dive into specific modules and certain workflows on a module by module tool basis. And then we also do live Q&A where we um, allow the ENERCALC engineering team to answer questions directly from the audience. So if there's ever a question that's too involved or it's going to require deeper digging and research, that's a better fit for the support team so they can investigate your concerns, look under the hood, and get more detailed answers. As a minor point of order, you will notice that everybody's microphones are muted just so we don't get any echo or feedback while Mac is presenting today. And as I mentioned, we do have open Q&A at the end of every office hours session, including today. So to submit a question for today's Q&A, just use the Q&A dialog in the lower dashboard of your Zoom window. If you experience audio problems at any point during the session, you can simply refresh your browser or jump out and rejoin the session. And if you ever want to rewatch today's program or share it with somebody on your team who wasn't able to attend, the recordings are always posted to the ENERCALC Office Hours playlist on our YouTube channel, which is also able to be accessed from our website on the Office Hours page. With that, I'm going to go ahead and hand it over to Mac to get going on our program for today.
Thank you, Seth, for a great introduction. All right, hello everyone, and I am excited to be back to be presenting the Office Hours program. So, without further ado, let's get this show started. So today we'll be covering a few things. This is the agenda. So we have a note on PDH credit for the Office Hours sessions, ENERCALC's latest build, what's new in ENERCALC, and of course our main topic for today is the composite steel beam module in ENERCALC, and we'll wrap it up with a live Q&A. So please feel free to drop your questions into the Q&A dialog at any point during the presentation. For our live attendees, we do offer a half-hour PDH credit. The certificate uses the name you used today when you joined the Zoom webinar, so feel free to adjust that now if you need to. Following this session, you will get an email with a link to download your certificate. And don't forget, the link to download the certificate expires in 30 days, so make sure you download the certificate right away. So starting off, would like to remind everyone to make sure that they are on the latest ENERCALC build. The latest build as of today is 2026 0720. So this is the July 20th build. ENERCALC releases monthly updates, and many of the support questions we get, missing features or mismatches between handcalcs and program output, come down to running an outdated build. So take a moment to check your build and update if needed to make sure you're running the latest and greatest build of ENERCALC. If you do not know what build of ENERCALC you're on, simply open ENERCALC and look at the top of your software and you will see the build listed at the top. If you are on an outdated build, you can easily download the latest build by selecting the update button in the upper ribbon right here. Once you click on that, you will get a new window, as you can see here on the left. What you can do here, you can check for updates. You can launch the for our users page to download the latest build. You can subscribe to new build update emails, which include release notes and highlights, highlighting newly added features, bug fixes, and other important updates. And of course, always make sure that this is checked, this option to get notified of new updates at program startup. Always make sure that this is checked. So as you can see, if you go to our website, that's what it would look like. And again, the latest build of ENERCALC is 2026-0720. So for those who haven't been working with the latest and greatest or haven't had a chance to look at some of the new features that ENERCALC has, I wanted to highlight some new functions and some of the new things that we added recently, so you can take advantage of that. This was highlighted last month, and I want to highlight it this month because it's a really cool update that I'm excited to share with you, and that is the reference loads in the project load group builder. So the wood beam, the steel beam, the concrete beam modules, as well as the composite steel beam module and the steel beam with torsional load modules now support the reference. You can that now it supports the ability to reference predefined load groups from the project load group builder directly into your calculations. So changes made in the project load group builder automatically populate every calculation that references those loads, and the status badge monitoring system notifies the user when referencing calculations need to be updated. So the project load group builder is can be found under the general tab right here. So let's take a look at that and see what it does. So when you open the project load group builder, you'll find yourself at this landing page right here, where you can pull from ENERCALC supplied or user-defined load items to build load groups. So you can see here we already have some information here for you, like the weight of certain materials, but you can add more to it and build your library as you need. Furthermore, you can create area loads, line loads, and point loads or point load groups. Once you have those load groups created, you can reference them in the future in your calculations. So for example, if you always have a floor load of 40 PSF dead and 40 PSF live, if that's something that you find yourself doing all the time, then you can simply just create a typical floor load right here. And then in the future, all you need to do, you just need to reference that load instead of manually having to input that load in every single calculation. Currently, reference loads are supported again in the wood, steel, concrete beam modules, as well as the composite steel beam and the steel beam with torsional loads modules. If you open any of these supported modules and navigate to the span load tab, which is the tab where you input your loads, you will see a new tab right here that says reference loads. Here we can select the load type. You can see here you can put a reference point load or area load or whatever. So you can select the load type, and that will open the same window that we looked at earlier. So you see we have typical floor load, you have typical roof load, and you can add as many as you want, and you can make them as unique as you want. And then once you click on it and you add that selected group, then it will automatically populate inside here. And you can see here they're grayed out because you can't adjust them because they are linked to that master load that you have in the reference load group. Calculations that have reference loads will include a status badge in the project manager. So you can see right here, you'll get these status badges. And when any change is made to the reference load, so let's say we're changing from 40 PSF dead to 50 PSF dead. As soon as you change it there, then every calculation that uses that reference load will be flagged. So this way you will know that those are the affected calculations, and you can simply just retrigger the calculations. The way to retrigger the calculations is the same way that we trigger recalculations for linked loads. You can recalc these calculations in bulk by just clicking on this button right here. So this is, of course, an exciting update, allowing users to create typical load groups that can be referenced across the calculations in their project, and of course, bulk update them in case particular flow loads change or you want to implement that change in multiple calculations. Another exciting update is the adjustable load graphics, is the ability to adjust load graphics in some of our beam modules. So steel beam, wood beam, concrete beam now allow load graphics and labels to be adjusted in the 2D diagram. This, of course, will help users manipulate the annotation so that the numbers are not overlapping and everything is easily legible and you can read it clearly. This is how it used to be, as you can see here, and that's what you can do. So to do that, users now have these toggles in the lower left-hand corner of their 2D tab, and you can see here it moves it up or down, so you can kind of click on the load that you want. For example, this one, and you can click on bring it up, so it brings it all the way up right here, so you can see things a lot clearer, and again, just makes things a lot more legible. Furthermore, we recently added a filter in that same tab, in that 2D tab. So we added a filter that helps the users display the specific load type they want. So loads are grouped by load type. So you can see here the loads that were applied, the loads all span, the span loads only, the non-linked loads, and the linked loads. So you can filter the display here just to show the loads that you want to see if you're trying to isolate a specific group. Last month, we shared that the access to Jack was now available in ENERCALC, and this month we are excited to share another update. The Ask Jack button on the main toolbar now opens a dedicated window, which provides a direct access to Jack, the ENERCALC AI support chatbot, without requiring a web browser or navigation to ENERCALC.ai. Jack is trained on ENERCALC documentation and product data, so he's a great resource for quick answers anytime you need them. We've made some recent updates to the building code information window, including new tabs to keep things better organized and more intuitive. All governing codes and material design standards can now be individually selected, so you can mix and match codes and standards to meet your jurisdiction's requirements. There is also a convenient sync button right here, as you can see, this big button, to bring all standards back in line with the selected IBC. Another update, of course, we've been talking about this for a while, and I'm still surprised that I still meet people who are not familiar with load linking, but I'm pretty sure here most people who attend office hours regularly, they know about it all too well. So the load linking is currently available in steel beam, steel beam, wood beam, steel column, wood column, and general foundation modules. This gives the users the ability to automatically link reactions from one calculation to another and the ability to change something in one member and have the effects of that change trickle down to all of the downstream supporting members. And if you haven't tried load linking yet, and you'd like to learn more about it, we have a YouTube playlist with short step-by-step videos to help you get started, and that's those videos right here. And then we have another video at the very end, and that is a full practical example of how to use load linking to transfer reactions from beams to columns, covering both materials. So if you have a wood beam sitting on a steel column, or maybe a steel column or a steel beam sitting on a wood column, and so forth. ENERCALC for Revit also has seen some new features recently. EFR now includes the wood column module, along with support for engineered wood sections, such as LVLs and PSLs and glue line members. 2 months ago, Seth presented on EFR for wood buildings. If you missed that session, I'll definitely encourage you to check out the recording to see these new features in action. So moving on to our main event, the focus of our presentation today is the design of the composite steel beams using the composite steel beam module in ENERCALC. So we'll be covering the module's capabilities by walking through an example together. So here's a quick overview of the capabilities and features of the composite steel beam module. It performs analysis and design of shored and unshored composite steel beams, supports solid slabs as well as slab on metal deck for composite design. A design full composite, or tells you minimum number of studs, or also you can the user can input a specific composite percentage that they're trying to achieve. Just to give you a greater level of flexibility. It analyzed the pre-composites as well as the post-composite states for unshored design, and calculates deflections using dissections, moment of inertia, as well as lower bound moment of inertia for accurate deflection calculations based on when the load is actually applied. So in today's example, we need to design a composite steel beam system with 3-inch normal weight concrete over 2-inch full craft VLI metal deck. So it's a 2 VLI metal deck. So the total depth of the assembly is 5 inches. It's 3 inches concrete and 2 inches metal deck. We have here the other thing is that the deck is perpendicular to the beam. So that's the condition that we want to examine. Effective width for the composite beam is 6 feet, and this needs to be unshored design. And the effective width, we went through the calculations of determining what the effective width is, and we will walk through this process shortly as we go through the example, but the effective width is indeed 6 feet. Again, and this is an unshored design. The beam span is 24 feet, and the trip width is 8 feet. And as far as the loads, what we want to work with is that we need to design the beam for pre-composite loads that will be removed before curing of concrete, meaning that this load is not permanent. This is just a construction load of 20 live and 20 dead. Then we need to design the beam for permanent post-composite loads. Those are the service loads later. That would be 40 live and 40 dead. 40 PSF live and 40 PSF dead. And lastly, we want to make sure that we include the self-weight of the beam as well as the self-weight of the slab, which will apply to the pre-composite state and will remain permanently applied on the beam to the during the post-composite state. So that self-weight is something that's going to be applied early on, and it's going to stay forever. The construction loads are only applied to the pre-composite, and finally, the final design load, which is 40 PSF live and 40 PSF dead, will be applied to the post-composite section. So to start a new composite steel beam calculation, we follow the same familiar process to start any module. We click on the Add button right here, then we navigate to Beams, and finally click on Composite Steel Beam. We're going to start with our inputs in the general tab, and we will work our way through the inputs, moving, of course, from left to right. So starting with the general tab, first we want to give our calculation a name. I have the most generic name here, which is CSB1, Composite Steel Beam 1. So that's what we're calling it, but for your project, you probably will have something a little bit more unique. Next, we cover some basic design parameters. ENERCALC can design in both ASD and LRFD methods. We will be using ASD for our example, but if you are designing LRFD, you can just simply click on this option. So we're clicking on ASD. Next, we need to examine FY and modulus elasticity of steel. We are planning on using a W section, so FY is 50 and modulus of steel is 29,000 KSI, so that stays the same, but you have the option to change these numbers. Those are user inputs. Last item in this block here is the maximum allowable deflection ratios. We want to use L over 180 for pre-composite, and we will use L over 360 for the transient loads, which is live load that we have in this case, and finally use L over 240 for the final total load in the post-composite state. So those are, and again, this criteria is just what I have for this example. You can change these as you see fit. Those are user input. Now let's provide more information regarding the framing assembly. We have 3-inch concrete over 2-inch metal deck. That means a total slab thickness of 5 inches. We also have determined the effective width to be 6 feet. AISC provides a simple process to determine the effective width, and it depends on the overall framing geometry, such as the total span of the beam, the spacing of the beam, and the distance to the edge of slab. For a quick refresher, you can click on this button right here, and this will display this window with the AISC code reference language to help you navigate the process of calculating the effective width. And you can see here, you're picking the smaller value of these three. And what's important to know here is that, again, we're using 6 feet. After going through this process, 6 feet is the number that we want to use. Next, we have the option to specify the use of a metal deck. If you uncheck this box, the calculation will be performed as if you have a 5-inch solid concrete slab. So let's see what that looks like. So the user interface will look like this if you uncheck this option. You will notice here that on the right-hand side, since you don't have a metal deck, this is completely out. This is no longer an option. And then you can see here, this is the 2D diagram that ENERCALC displays, and this is the 3D diagram or the 3D visual that ENERCALC displays. You can see that this uses the full slab and it shows it as 5 inches with an effective width of 6 inches. And in 3D space, you can see that this is a solid slab. Since our example is utilizing a metal deck, we will check this box, of course, and the user will have the option to input their own rib measurements for the deck. This means the user will manually input the rib height, spacing, the width at the top, and the width at the bottom. You can do this, and ENERCALC will use these numbers. Alternatively, if you click on this button, you will get access to a database of many of the popular metal deck products grouped by manufacturer. In the database, we already have the Volcraft decks. You can see here Volcraft 3 VLI, Volcraft 2 VLI, and it has all of that information pre-populated. You see that? So we will just pick this deck since it's already there. But if it's not, then you can just put your own numbers right there. So for us, this is the 2 VLI, that's what we need. So we just select it, and all these numbers will be auto-populated properly. So now we have to specify the deck direction. If it is perpendicular or parallel to the beam, or if it is a transition beam where the deck changes direction. The deck in our example is perpendicular to the beam, but it is worth noting that all the results, as well as the 2D and the 3D visuals in ENERCALC, update in real time as you make changes. Also, the 2D and the 3D visuals are an accurate depiction of the input information. This means if I click on perpendicular, you can see that this changes. This shows a 3-inch concrete because it ignores the deck below it, so it ignores the 2 inches below, and that's in the case of perpendicular, and you can see it here shown properly in 3D, the 3D visual. If we pick parallel, you will see it shown right here in the 3D space, as well as in the 2D diagram, you can see that it uses the full 5-inch concrete and it populates it right here. So we now need to determine, and I want to just confirm that, because our project is, or our example is a perpendicular deck. So that's what we're using. We're just clicking on perpendicular, the deck is perpendicular to the beam. So this is the option that we're using, and that's what we're using in this example. So now we need to determine if the construction is shored or unshored. If you pick shored construction, then there is no longer a need for ENERCALC to run numbers on the pre-composite state. Because remember, the pre-composite state is to see if the steel beam by itself is capable and sufficient to take the construction loads, without excessive deflections or without breaking, or without failure. So if the construction is short, then the idea here is that the beam is sufficiently short that it will not fail. It will not experience excessive deflections. Hence, there's no reason for us to be running any numbers on the pre-composite state. And all that ENERCALC will examine is the post-composite state, the final state after the concrete cures. Short construction, of course, it's expensive, and most engineers don't design with short construction, or for most projects, at least here in my experience, Oklahoma, Texas area. So what we choose here is the unshored construction. So because it is common to have unshored construction, that's what we're using in our example. So we are going to be clicking on this option because now we want to sequence our load and we want to make sure that we are checking the pre-composite state for strength and deflection. And then once we're done, we will be checking the post-composite state for strength and deflection. Now we move on to providing more information about the studs. You can pick the stud diameter from this drop-down menu right here. Our example is using a 3/4 inch diameter studs. The next item right here is the stud capacity. This is the stud shear capacity. I'm going to skip over this for just a second and move on to the next one. This is the concrete F prime C. This is a user input. You can put whatever F prime C you want for your concrete. I'm using 3 KSI. You can use whatever you have in your specifications or in your design. Same thing for concrete density. I am using 145 PCF for concrete density, and this will be used for modular elasticity calculation for the concrete. Now that we've gone through the others, I want to get back here to QN, which is again the shear strength capacity per stud in kips. The user has the option to input their own number. So it's important for you to know that this is not a locked cell. You can put whatever you want right here. You can put 2 kips, 5 kips, whatever you want. So for example, if you want to put 15 kips, you can, 14, whatever it is, it'll be just fine. And ENERCALC will run the numbers, will perform the calculations based on that stud capacity that you provided. Alternatively, ENERCALC can help you calculate QN if you haven't calculated it, or if you don't have the number right off the bat. So if you click on this option right here, you will get this stud capacity calculator, and this is per the AISC. So this QN equation, this is right here. This is the QN equation, has a few things that it needs to know in order to run the numbers. So the area of the stud, this is based on the stud diameter that we chose, which is 3/4 inch. So that's auto calculated. The concrete strength, we're using 3KSI, and that's because we already populated it here. That's why I wanted to do the other things before QN. This next thing, the module elasticity for concrete, that's already been calculated based on the concrete density that we input right here. And then the next item is the FU of steel, of the stud tensile strength. That is a user input because there's nowhere for it to find that out. So 65 was the default value that was used. I'm okay with it. If you have different grades, you can use it. Then we get to the next part right here, which is the RG and RP system configuration factors. To understand this further, the user will need to refer to the AISC table I8.2A. This is, to make life easier, this is the table that I was referencing, and we have it right here. So this is the RG and this is the RP. So RG is based on many factors, such as deck orientation, as well as the number of studs per rib and rib dimension aspect ratio. RP is also based on many factors, including the deck orientation. So in our example, the deck is perpendicular, and we have one stud per rib. That means RG is 1 and RP is 0.6. Keep in mind, there is a footnote. This is footnote B. There is a footnote regarding the RP value, which could possibly increase it from 0.6 to 0.75, but I am not examining that footnote for the purpose of this example, and I will be using the standard value of 0.6. So with that, if you see here in our little calculator, RG, you have a drop-down menu that says if it's 1, if you have a perpendicular deck, and you have 1 stud per rib. This is important. Perpendicular deck and 1 stud per rib. So we already have that. So we click on it, and then RP is 0.6. So we're good to go. It does the calculation for you, and pretty much it came up with QN equals 17.24. If you like this number, then you can click OK here, and it will auto-populate it for you right there as an input. And again, if you don't like this number, if you want to use 16, if you want to use 20, whatever you want to use, you can simply just delete this and put whatever number you want, and you don't have to worry about the calculation. Last but not least on this tab, we need to determine the desired composite action percentage. We can pick either full composite, so we want to achieve full composite, or you can say calculate the minimum number of studs, or you can say I want a composite percentage, and you can then input that percentage right here, 50% or 60% or whatever you want. For our example, I want to achieve 50% composite action. So I'm just putting that right here, and this concludes all of the input data that we have here under the general tab, and we are ready to move to the next tab. So the next tab is the span and section data. This is pretty straightforward. From the example statement, the span is 24 feet, so put that here. And now we need to pick a size to start from. You can select the section type. We will be using a W section, and then from the bottom left side right here, we can select the beam size that we want to use. I'm going to start with a W12 by 22. This is the size that I'm using. If you want more shapes and sizes, you can click on this lookup button right here, and that will give you a larger database. You can see additional types such as C or MC, as well as different editions of the AISC. The user can also use a user-defined steel member instead of using a standard section. So maybe you have a built-up section where you have something different. You can define your own. That's a user-defined, and you can have something completely different. And ENERCALC will still run the same code checks on that size member that you have predefined. In our case, based on our example, we'll stick to using a standard section. And again, we're starting with a W12 by 22, and we are ready to move on to the next step. This is where the fun really begins, in my opinion. This is the span load step. First, the user can choose to allow ENERCALC to auto-calculate and include the self-weight of the beam. And in a separate option right here, it allows the user to auto-calculate and include the self-weight of the slab. For this example, we want to enable both of these options because remember, we needed to include those. And however, for ENERCALC to calculate the weight of the slab, it needs to know the slab trip width. And in this case, since the beams are spaced at 8 feet on center, then the slab trip width is 8 feet. And the slab weight is, of course, the 145 that we predefined previously under the general tab. And I want to make sure that it is clear to not get the slab trip width for weight calculation, which is 8 feet. We don't want to get that confused with the effective width of 6 feet that we have. The effective width, this is for the composite section calculation. That's the effective width that's from the concrete that's being engaged with the steel. The other one, this is for weight calculation. So the beams are spaced at 8 feet on center. Then the trip width here is different. They might be the same in certain cases, but they might be different. So that's why you have a different input here that you can put this one right here for slab weight calculations. So now that we have included the weight of the beam and the weight of the slab, we are ready now to input more of our loads. The process to apply loads in all of ENERCALC various modules is very similar. The user can apply, point loads or fully or partially uniform distributed loads, trapezoidal loads, etc. But before we can move forward with applying these loads, we need to understand the 3 load application types that ENERCALC offers specifically for this module. So this is where things diverge a little bit, where things differ a little bit. So because the composite steel beam module has a pre-composite calculation and a post-composite calculation, we need to tell it which loads apply to which state. So to understand this load application better, I figured we discuss the options in conjunction with the loads that we have in our example statement. So I included the loads on the top left right here. To remind you, we have a pre-composite construction load that will be removed before curing of the concrete. That's 20 live and 20 dead. And to remind you again, post-composite, the final load that we want this assembly to handle is 40 PSF live and 40 PSF dead. And of course, we have the self-weight of the beam in the concrete that's going to be applied pre-composite, and it will stay forever. So the cool thing is that ENERCALC automatically categorize the self-weight of the beam and the slab as something that's applied to the pre-composite state, and then it will be applied to the post-composite state. So this is ENERCALC automatically does this for you. You don't have to worry about it. But if you have any other load that's applied pre-composite and staying post-composite, you can apply it and choose one of these 3 options, which we will dive into here shortly. So without further ado, now that we reviewed the loads that we have, let's start looking at these loads right here. So we have 3. The first two sets of loads is for the pre-composite load. So the load that we have is applied during construction to the bare steel section, and before the concrete cures will be removed. So that means before the composite action is achieved. This means that the steel section by itself needs to be strong enough to support this load because the concrete is still wet and no composite action is achieved. Also, that same steel section by itself needs to have an acceptable deflection level under the construction load. So for this case, ENERCALC provides these two options. First option is the load applied to pre-composite section, meaning it's applied to just the bare steel, and it's removed before the curing of concrete. And that's why it says applied to pre-composite and removed before curing. The second option is a load that is applied to the pre-composite, meaning to the steel by itself, because the concrete's still wet, so we can't rely on any composite action. But in this case, the load will remain after curing. The first option is a good option for construction load because the construction load is applied pre-composite, and then once they're done, once they pour concrete, everybody's going to leave. They're going to take their equipment. Everybody's going on their own. So that's where the load ends. So it's applied pre-composite and it's removed before curing. So this load, the 20 PSF and 20 PSF, that's this load application. The first option is the right application for it. And of course, we have a tributary width of 8 feet. That's the distance to the adjacent beam next to it. Now, this second option is a perfect use for self-weight. Self-weight is something that is applied pre-composite and it's remaining after curing. So then once it's applied, it's never going to go anywhere. So again, if I did not automatically let ENERCALC calculate and apply the weight for me, I would have put it under this criteria, under this option right here. So that takes care of this load right here. Now we are ready to move on to the next load. So we have to apply 40 dead and 40 live, and that is the permanent load. That is being applied later when the concrete cures and the composite action is achieved, aka the load is applied at the final state. So for this load, it classifies under this. It's applied to post-composite section only. That load is applied later. So lastly, at the bottom, you can find a summary of all of the summary table of the loads that you applied. And you can see here this load, the 2020, that's pre-composite removed. And the other load, the 4040, is post-composite only. So now that we're done with this load application, we are good to go. But there's one more thing that I want to show you, and that is this new tab, the reference loads tab. Remember earlier we talked about the project load group builder. That is now implemented in the composite steel beam. So if I already have a set of load that I already predefined that says floor load or says third floor load or something like that, that has everything that I need, I could simply just bring it in and assign a load application to it rather than having to type, 40 live, 40 dead, and so forth. So if you already have that load, if you're using the load group builder, the project load group builder that we talked about, the new feature that we recently revamped, if you are working with that, then know that it can be applied and you can just pick whatever load you want from your reference library. So since we don't have any reference load, we're ready to move on to the next tab, and that is the load combinations tab. This tab is the same familiar tab across all of the ENERCALC modules. You strength strength load combinations, then another set for reaction combinations, and then another set for deflection combinations. This allows the user a great level of flexibility, and of course the user can easily add, modify, or delete any load combination, as well as selectively pick any load combination right here and turn it on and off. So if you don't want to run this load combination momentarily or temporarily, if you don't want it to run, you can just turn it off and see what the results look like and then turn it back on and so forth. So now that we have entered all of the required input data, we can check out the results. Under the summary results tab, you can practically see all of the critical stress ratios. First, the max bending stress ratio is at 0.718, which is of course less than 1.0, so we're good to go. You can see the composite percentage, which is 50% as we selected, so that makes sense because we're we forced it to be at that percentage. Then you can see the maximum applied moment and the allowable moment capacity. Then you have info about the pre-composite max applied moment and the pre-composite steel section allowable moment capacity. And that makes sense. This is important because this right here, the pre-composite, this comes from two elements. Element number one, or two sources of load. The first source is the self-weight of steel and self-weight of slab. The second source is the construction load. So that's applied just to the steel beam by itself. And you can see it right here. That's the max moment applied, and that is the maximum capacity or allowable capacity of that steel section by itself. However, this one is the composite section. This is the final post-composite state. So you can see here the 75 kip feet comes from the self-weight and from the final post-composite load of 40 psf live and 40 psf dead. This does not include the construction load because the construction load never made it to the final state. And this again, this is the allowable moment capacity based on the composite section after achieving 50% composite action. Next, on the right-hand side at the top, you can see the maximum shear stress ratio, which is 0.197, of course, less than 1. And then lastly, we have deflection checks. There's all kinds of deflection checks here. So the first set is the total maximum deflection. This includes the deflection that occurred before the composite action and the additional deflection that occurs after the post-composite loads have been applied. So if you remember the pre-composite, you have the construction loads, but those are going to go away. So you can, we ignore the deflection from that. But the self-weight, that's staying there. And the steel is going to deflect. And that deflection is permanent. It's there. So once it achieves the composite action, then the new loads, the 40 psf live, 40 psf dead, come in play. Then the new deflection is additive to the deflection that occurred due to the self-weight of material when the steel was just by itself. So the first portion, the pre-composite, gets the deflection gets calculated based on the steel moment of inertia, and then the post-composite deflection gets calculated based on the lower bound moment of inertia. So that's the composite, the full composite section, and then finally those two deflections are additive. So we add them together, and that will give you this this number right here. So that is the first part. Then the second part, you have the transient load, and in our case, that's just the live load. So it still meets the deflection criteria. This is the criteria for the total load was L over 240, if you remember, and the criteria for the transient load was L over 360, and it meets that. And lastly, the pre-composite maximum deflection. This includes the deflection due to the this one right here is construction loads plus self-weight, because we're trying to see how much this deflects under construction load. So there's the pre-composite. So you'll have that, and that was L over 180. And of course, it still meets this criteria. A much deeper deflection analysis and incremental analysis values along the length of the beam can be found under the deflection tab. You can pick pre-composite total or final composite or whatever load combination set you want, and you can see here a lot of intermediate values and deflection along the length of the beam for incremental analysis. Another useful tab is the property tab. You can find more intermediate values, but one value that's very useful is the location of the plastic neutral axis based on the composite action percentage. So for example, based on a 50% composite action, you can see that PNA is in the flange, and the location of the PNA from the bottom is at 11.898 inches. So of course, as you go down here, let's say a 40% composite action, your PNA is in the web, and that's its location. So you get a lot of useful information in here. There's all kinds of other information that I'm not going to go through now, but this is a useful tab if you are trying to review or get some intermediate values. Last but not least is the studs tab. This is the tab that tells you how many studs you need. According to this, we will need 10 studs from 0 to the maximum moment location, which is in this case is the midspan. So that's at 12, that's at 12 feet. So from 0 to 12, you need 10 studs. And then from 12 to 24, which is the other half, you're going to need another 10 studs. So from 0 to 12, 10 studs, and 12 to 24, 10 studs. This is critical here to note that based on this, we can fit one stud per rib without problems. So our original assumption is correct for the RG. Remember the system configuration, system factor. RG was assuming that it is one per rib. If you remember here, that's why we got RG of 1 is because perpendicular to deck, so that's still accurate, and it's one stud per rib. That's accurate. If you need more than one stud per rib, then that will kick you right here, for example, and that will put you on an RG value of, instead of 1.0, it's going to be 0.85, which will reduce the QN for your stud. It goes from 17 to 14. But since you have two, probably you're okay, but this would be something that I would rework once I realize that my solution is telling me to put two studs per rib, then I will go back, change the RG value to 0.85, recalculate QN, put the new QN, and let ENERCALC run the numbers again to make sure that we are that everything is accurate and your beam still passes and it does not fail or doesn't create any more issues. So overall, this is what we got. We got this is the final assembly, 3-inch normal weight concrete over 2 VLI deck. Total thickness is 5 inches. W12 by 22 works. 50% composite action with 3/4 inch diameter studs. 10 in the first half and then 10 in the other half. And then here, this is the allowable moment capacity, and we were able to achieve the maximum total deflection. It was 1.094 inches, and it's within the L over 240 criteria. And lastly, the max pre-composite deflection, it was 1.21, and that is meeting the L over 180 criteria. So that concludes the composite steel beam example. I just have a couple more things to go over, and I want to then we'll open this to live Q&A. I just want to share with you that we have a growing library of verification calculations. You can navigate to it on our website. You just click on for our users, then under documentation, and then click on verification calculations, and that will take you to the page. And you can see that's what it looks like. That's what a calculation verification looks like. And then it shows you what it looks like from ENERCALC, and then you can match the values. And what I'm displaying right now is the wood column calculation, but we're adding more as we go, and we already have a few here. One more thing to note is that today's session, as well as all of our previous office hour sessions, are recorded and uploaded to our website. You can simply visit enercalc.com/office hours and scroll down, and you will see all of the recordings in chronological order. So the last one was from July 8th, the restrained retaining wall presentation that Chelsea did last month. And in a couple of days, we will have another box right here for today's recording and so forth. And we have these recordings going all the way back to the inception of the program back in May 2024. ENERCALC has been making it a priority to attend a lot of local events and support local structural engineers associations. And we want to talk directly to our users. Our upcoming event, we have the Structural Engineers Association of New Mexico. That's actually tomorrow, and we already have an engineer on their way there. And then on August 26th is the Structural Engineers Association of California. So we're going to be there, a couple of our engineers as well as our CEO. And on September 10th, the Structural Association of Ohio will have one of our engineers attending there. So if you are around, make sure you come and say hi and put your name in the raffle and see if you might be a lucky winner of one of our engineering themed custom made Lego sets. And with that, we are ready for Q&A.
All right, let's get into it. We got a lot of great discussion for you today, Mac. First question, circling back to the project load group builder. Do the reference loads stay resident in the program or are they project specific? So it's kind of a two-part answer to this. So the load groups that you build are project specific. So that means you can define load groups, um, typical classroom floor loads, roof at balcony, so on and so forth on a project by project basis. And then the load items list is user specific, which means it's on your local machine and you can use the same load items from project to project. So feel free to get in there and explore that and ask us if you have more questions or want to drill down on that. But that's out in the wild now, just like load linking is. So if you have the latest, greatest, you can jump in there and explore those features. And then always feel free to reach out if you have further questions. Next question. What are the PDH hours for? So PDH is professional development hour. We offer a half hour of professional development hour certificate because that's basically the guaranteed technical training portion of the session, whereas there's other, housekeeping and what's new and that kind of stuff. Professional development hour is a certificate to show that you've had technical training, which some jurisdictions, many states throughout the United States require for renewal of a professional engineering or structural engineering license. So that's what that's all about. It's just a nice benefit that we offer to our users, many of whom are maintaining licenses in multiple states. All right. Next question. Can self-weight also include the weight of the metal floor deck? It's relatively light, but it is a permanent dead load. So, Mac, you touched a little bit on questions around self-weight. This is an interesting question because it's not explicitly considered automatically with the touch of a button or the check of a checkbox, but you do have the options to accommodate that. So it sounds to me like the question is when you tick that checkbox to say automatically include the weight of the slab, does it also include the weight of the deck? At this time, it does not, but you can manually impose that load if you need to. Mac, do you want to hop back to where we were looking at that load input?
Here.
Yeah, there we go. So in the upper left-hand corner, you do have a checkbox that says automatically calculate and include the slab weight.
Yes, but that
That
does not
is,
include
that's right. That's
the
the literal weight, self-weight of the concrete over the
yes,
tributary width that you impose there.
correct.
Um, you can
But if
always
you,
manually
yeah,
impose a line load that uses trib and uniform area
uh,
magnitude if you wanted to include that very small additional amount for the deck itself.
oh yeah, that's exactly the weight of the metal deck itself. I don't know, the 1 or 2 PSF or however it
Yeah.
weighs. That's not included here. If you want to, you can apply it, and you can see that's why you have the option apply to pre-composite and remains after curing. So this is part of the
Yep.
permanent structure. You can just add a load and put a 2 PSF dead load, and it'll stay there forever.
Yeah. Here's an interesting question, Mac. Can I somehow take advantage of the floor profile and beam sizes my team already created in Revit?
Can you repeat the question? Sorry.
Is there any way to take advantage of the floor profile and beam sizes my team already created in a Revit model?
Yes, you can, if you have ENERCALC for Revit, you can just design this completely from within ENERCALC, from within Revit, and it will auto-populate, most of this for you, geometry and deck type, all of that stuff, and including the loads if you already have the loads.
Yep,
So
absolutely. So for
absolutely.
those who aren't familiar, ENERCALC for Revit will let you basically set slab properties, set beam properties, and then for every beam in that floor system, you can just automatically create calculations on the fly and share those properties across a large floor area.
Absolutely.
Next question. For the pre-composite loading removed before curing, I understand removing the 20 PSF live load, but what is the 20 PSF dead load you've selected? What would a pre-composite removed after curing, dead load before. Mac, this is a reference directly to your example.
Yes. I think this is part of the example that I think eh, my examples try to illustrate the various ways of using this. So what we have right here, we have separated the construction load from the final load. So some people say you have a pre-composite construction load of 20 PSF, and this 20 PSF will be removed later, and then we're going to get a new 40 PSF load that's going to stay after curing.
Yeah.
Some other people say, well, I don't want to consider it that way. I want to consider 20 PSF permanent from start to end, and then the new load that comes after composite is just an additional 20. Does that make sense? So you
Yep.
can you can split it however you want. I just made a clean split, but in reality, this 20 PSF that's acting as part of the construction load now, it's really staying forever and it's becoming part of the post composite. But splitting it like this is just it makes it a clean finish. I'm designing for 20 and 20 construction loads, and that's what I run my pre-composite section on. And then for my final composite section, I need to run it for 40 and 40. But you do
Yep.
whatever you
Yep.
pick whatever option that makes sense to you
Or
and
yeah.
workflow.
Or alternatively, you can also use the pre-composite remains setting.
Yes, exactly.
Yeah. Yeah.
The
So mainly
pre-composite
he's
remains,
just
yes.
Mac is just showcasing the capabilities you have available, whether or not it's applicable in your project. There also could be circumstances where you have staged materials on the slab during
Absolutely.
curing that gets removed afterwards that you want to treat as a dead load instead of a live load. There's just showing that the program has those capabilities. So slightly related to our question about dead load and beam self weight and slab self weight a second ago. More explanation on trib width and slab span. So I assume,
Yeah.
and Mac, feel free to jump back to the program or jump to slides if you want to. I'm going to assume that this is drilling down on the distinction between slab effective width versus loading tributary width. So Mac, do you want to kind of go at that for a second?
Yes, that's exactly what this is. So from AISC perspective, whenever you have composite beam design, if you have a slab that sits on top of a beam, what is that width that's actually engaged and is part
Yep.
of the composite
How
section?
much of the slab do you get to use in
Is
compression
yes.
to
Yeah,
build a
how much of the
composite?
slab is actually helping you and it's
Yep.
engaging. And that is something that AISC tells you what to do. You have to use the smaller value of the following, and that is 1/8 of the beam span. So 1/8 of the span of the beam is 24 feet. So you get 1/8 of that, or the distance to the slab edge in case you are at the end of at the edge of the slab, or half the distance to adjacent beam from both sides. So in this case, what we have right now, the smaller number, 1/8 multiplied by 24, that will give you, yeah,
That's
one
it's
eighth
each
the beams,
side.
yeah, each side. So that's 3 on one side, and then you have it from the other side, that's 6. Unlike this one, the half the distance to the adjacent beam, half is 4 and the other half is 4, so that's 8. We're required to use the smallest value for this portion right here, for what's actually being engaged as part of the composite section.
Yep.
Now, from a weight perspective, this is just simple tributary when it comes to knowing how much weight you're supporting. That one is just, the distance between the trip between this beam and the beam adjacent to it on the left and the beam adjacent to it on the right. That's half here and a half here. So that's the 8. That's where
Yep.
the 8 comes from here.
Yep.
So it depends on what you're trying to do. This is very similar to, concrete with a T section in concrete or something like that. So very, very similar style. How much at the top is actually effective and it's part of your assembly.
Yeah. But the main thing is you have complete flexibility to specify
Yes.
your composite section effective width and your loading tributary width separately. They're related. In both cases, they're related to the geometry of the framing system, but they're distinct from each other. You can control them individually. And as you create your loading, you can even create multiple loading items that have different tributary widths on an item by item basis.
Yeah.
So, all right, good question. Next question. Questions in response to the value chosen for the effective width variable. We just touched on this, Max. So the question is about that 6 feet, 24-foot
Yeah.
span, which would make the effective length 24 over 8 equals 3. That would be
Yep.
for one side of the beam, but the AISC criteria specifies those three different things you choose from define the effective width each side of the beam, because in some cases it has to do with distance to adjacent beam or something, and so that distance wouldn't be the same on both sides. So you calculate for one side, then for the other side, add them together. That gives you the total effective width of 6 feet.
Absolutely.
All right, next question. Does the program consider any ponding of concrete under pre-composite deflection? Is there a way to check with extra concrete for a flat floor? So this is an interesting question, and it's definitely something that always comes up when you're doing composite. The ENERCALC composite steel beam module does not explicitly consider any phenomenon associated with ponding or with uneven distribution of concrete automatically on its own. You have the ability to auto add self weight. You can use all the different controls that Mac already showed you guys. If you have a situation where you're concerned about uneven distribution, you obviously can use the built-in capabilities in ENERCALC like Mac has on screen right now, where you can do trapezoidal loads, you can do segmented loads with different magnitudes along the length of the beam. So you have the ability to simulate an uneven distribution if you feel the need to do so. This module is not automatically doing any of those phenomena for you. Go ahead, Mac, if you want to add more on that.
Yeah, I want to show right here, make this bigger. If we can, I'm separating this. You see that? So if you have ponding issues due to that deflection and, or you have, uneven distribution due to ponding and you have extra weight of concrete, you can manually simulate that similar to what Seth was saying. I added a partial uniformly distributed load here, for example, to account for that. Or you can do a trapezoidal load if you really want to, if you have a bigger problem and you want to be a lot more accurate. So, but yeah, it wouldn't ENERCALC doesn't automatically address this. But if you know that you have the extra load and you have the problems, you can just put that extra load as you need to, and you can apply it as applied to the pre-composite section, and it remains after curing. So that'll stay forever
Yeah.
there.
Yeah, and in most cases, the real secret sauce for avoiding problems like that
Um,
is trying to
Camber.
calculate your dead load deflections as accurately as you can during design so that you can specify camber on the drawings. Not too much, not too little, just enough so that you hopefully flatten out and get that neutral. Because I mean, there's probably quite a few engineers who've done a composite job and they got a panic call from the field and like, hey, we're trying to flatten out the camber. We don't have, you know, and ENERCALC itself doesn't explicitly address camber, but you can figure out your camber based on the deflection results that we provide. There's actually a question down below. Our very next question, Mac, has to do with camber in the beams. You can get an idea of what your camber should be from the dead load deflection results that ENERCALC produces. So that's one of the best ways to avoid the ponding situation or avoid your contractor getting into a situation where they're like, hey, we're trying to flatten out the beams. Now they're adding more concrete than you intended, so on and so forth.
Absolutely.
As a sensitivity analysis, does changing the effective width to 3 feet change the outcome of the design? Yes, it absolutely would.
Yes.
There's
Yeah.
several major things when you look at the fundamentals of steel composite design. There's several major things that are affected by the effective width. Obviously, first of all, that determines how much effective compression capacity you're getting from the slab itself, which changes the plastic neutral axis location. That's going to change your shear flow calculations for the stud design. Um, if you're trying to figure stud capacities or stud quantities, it also is definitely going to change your post-composite deflection results. So yes, absolutely. The effective width has a big impact on the calculated outcomes of the design. All right, next question. I used my initials when joining the webinar, not able to see the option to change my name. Please advise. Feel free to shoot us an email if, since we know you were here, just reach out. We can make sure that you get your certificate with the proper name. Although there should be, I think it's from the participants panel where you can see yourself and you can either click the three dots or something, and you should be able to rename yourself. I do believe you have that capability. I think it's on the participants tab.
And for the record, if that happens, especially early in the session, if that happens, you can always just log out of the session and log back in with a new name.
Yeah, it
And
usually prompts you to submit your name when you get into the session.
yeah.
All right, next question. Does the composite beam module calculate the exact composite percentage for the given stud design, or does it force me to assume one for design? Do you want to go back to that stud design
Yes, let
screen
me
that you were looking
open
at earlier, Mac?
this right here. So first of all, as you can see here at the bottom, the composite action, you can say, let me actually go back here. So you can say that you want to achieve full composite. And you can see here that the number went up to 166. And you can see that it's asking for, you know, this this many studs or whatever. So you can say calculate minimum number of studs, or you can ask for the percentage, and that's a user input. And for example, if I put, I don't know, 30%, maybe that's not going to be good enough, or then I increase it maybe to 50%, then that's good. Like I'm going to do this 25. Yeah, I don't have enough loads on this side on this beam. Let me make it. Yeah. So you can see here, at least it's failing deflection. You can see that capacity is 109 based on 25. But then if I do 50, this 109 will change to 134. So if I do 75, for example, it goes to 151 and so forth. And based on the percentage that you chose, it'll tell you how many studs that you're supposed to use. So for example, in our example that we used, I did 50% composite action, and it was telling me to use 10 studs. But now I changed it to 75. To achieve 75 composite action, I needed to use 15 studs. And then lastly, you can see this is pretty cool right here. This is the shear connector percentage, the composite action percentage. So this actually shows you everything. I know you didn't ask for it. You didn't ask for it to be 98 or 97, but it's showing you everything. So in our case, at 75, you can see it right here and you can get the values that you need. But if you're curious about what it looks like for something else, you can just go and look at this and see what you get. Or as simple as changing a number right here and say, okay, well, I want this to be 95 composite, and it'll run the numbers and it'll tell you, okay, well, you need 18 studs now to achieve 95. I hope that helps.
All right, next question. Can we use two span beams for composite steel beam analysis? The ENERCALC steel composite steel beam module has always been set up as simple span in order to make sure, and simple span with pinned ends to make sure that you only have positive moment. Obviously, the AISC process for steel composite, which we're implementing here, is focused on that top flange condition where we have shear flow with the slab. That doesn't apply if you have moment reversal where you get the bottom of the beam in compression. So the ENERCALC steel beam module, composite steel beam module, has always been single span only with pinned ends to make sure that you have only positive moment. All right, next question. Back to the project load creation. For the saved loads, is there a way to save a favorite or similar that you can apply to new projects by default? Yes, with load items, not with load groups, but the engineering team has made a note of that as a feature request. Good question. Here's another good question. When can we expect load linking integration for composite beams? So, composite steel beam load linking obviously is a different animal than all of the other load linking in ENERCALC because of the sequencing issues where you have your pre-composite loads that persist, loads that are removed. that's on our radar for something that we know customers are interested in. The development team is beginning to study that topic as well as the engineering team. So we'll be sure to keep you guys posted on that whenever we have something to announce. All right. Next question. Is it possible to use properties calculated using general section property calculator in a steel beam analysis imported? Not at this time, no. But if that's something that you have a use case for, um, we don't want to just like a knee jerk, oh, send a feature request. What really, really helps the engineering team a lot is for us to hear like a really detailed explanation of what your use case is, so we can understand what problem you're trying to solve. So yeah, if you have specific use cases, we definitely want to hear about that. Um, I think we've been asked that question before related to built up steel sections where someone's wanting to do a general section property calculator and then perform robust AISC section capacity calculations on an arbitrary section. That's a little bit of a difficult thing to do, but feel free to reach out to the support team um, to get more information about that. There is an existing feature request along those lines, but it helps the engineering team a lot to understand your use case.
I want to add one thing to that question, is that there is no way to automatically import it. But if you have, like, those are the standard sections, AISC standard library. But if you have done some work on a general analysis module, for example, and you figured out you need an IX of something or whatever, and you have information and you have a built up section, you can just get right here and click on user defined, and you can create a brand new beam pretty much where it has all of the information that you want to examine. So you can create your own beam with its own IX and its own um, area and all of that information that you need, its own depth. So this gives you some more flexibility. And again, as Seth said, we would like to know what's a little bit more details on what you're trying to do, but this might be also helpful if you just create your own beam right here. Once you know your IX and stuff like that, once you know it, you can create your own beam and then have ENERCALC examine it. Or the composite steel module can run the code checks on it.
All right, next question. Can you explain the pre and post deflection again? So post construction, will the actual deflection be the added numbers that were displayed pre plus post? So just briefly
Yeah.
revisiting that topic of loads, when Mac was on our loads tab, there's essentially three different categories of loads that you can apply, and the deflections are calculated accordingly using those same approaches. So you can apply loads that are on the beam pre-composite from the very beginning and they remain permanently. You can create loads that are pre-existing on the pre-composite section and they are removed in the final post-composite condition. And then you can also apply loads that are only existent on the final composite section. So the deflections are calculated along those same lines. So the the pre-composite checks that we're performing, basically the concrete is wet, right? And so it has no capacity, you have no composite action. So the steel beam itself has to be adequate for all of the pre-composite loads that you place on the beam. So all the dead load you place, the self-weight of the beam itself, the live loads that you place during construction, the bare steel beam has to handle that. And so those are the loads that we use to determine the pre-composite deflection that the beam undergoes, right? And then when you have your post-composite condition, now you have a composite section with capacity of the concrete and capacity of the beam. And so you have you're using the plastic neutral axis. We've got this composite moment of inertia for the section, the transform section. Under those conditions, then the beam is going to be subject to deflection caused by loads that were there from the beginning and persisted into the permanent condition, and loads that were placed only in the post composite condition. Um, Mac, is there anything you want to add to that? Is that a decent overview of what's going on there?
Yeah, that's a good overview, and I just want to jump and add just one thing. because he asked about the deflection specifically. So for example, in our case, in this example that we went through, the final the final deflection will be calculated. It's the addition of two things: the pre-composite deflection, but the pre-composite deflection, not for the temporary loads, only for the long-term loads that will persist all the way. Meaning self-weight will have a deflection in the pre-composite state that will be added to the deflection that will occur later in the post-composite state based on the live load. Now, if you had a construction load that was removed before curing, it was just put there during construction, and then the workers, left and everybody's done, then we don't have that deflection. So that won't be added to the final state. So in summary, yes, the final deflection is a combination or an addition of a portion of the pre-composite deflection plus all of the post-composite deflection. And if you click on this button right here, this is useful for all modules. But if you click on this button, this will automatically take you to our help page for that module. And it has a lot of good information, but the part that I want to highlight is this. This is a written description of the three. So those are the three applications. You can read the description here. If what Seth and I said, if that confused you more, then maybe reading it right here, that would be the easiest way to understand it.
All right, next question. Does the optimum design always turn out to be that the beam spacing is the same as the effective width? It's very difficult to generalize that because there's so many things that can vary from project to project. That's the interesting thing about that AISC formulation is that it includes not just the span length, also the spacing throughout the bay, um, thickness of the slab, and lots of different things. So it's very difficult to generalize and say for certain this is the optimal effective width. It depends on um, how thick the slab is, how much bending capacity you're getting out of the slab, how far out you can stretch your beam spacings, how much depth is available for your beams, and so on. So there's a lot of different. That's more of an engineering judgment and experiential thing than a software thing. Um,
Yeah. And in our example right now, actually, it's not effective. It's not the most optimal to keep the trip and the effective width the same because the effective width right now, it's only 6 feet of the slab that's engaged, but the beams are spaced at 8 feet, and I'm still at a decent capacity. So in my case, if I made them 6 and 6, I would have had a problem right here. I mean, not had a problem, but I would have been more conservative. So I don't think that the two are tightly related as much as you have to look at the overall geometry and the span and the
Yeah,
loads overall.
exactly. They're not always tightly coupled. In my experience in designing steel composite floor systems for everything from office buildings to heavy commercial and industrial uses, um, a lot of times when you're using steel composite, you're getting more work out of the slab. And so oftentimes you're going to stretch out that beam spacing
Exactly.
and let the slab work a little bit harder. And so in those cases, it's actually a little bit rare to get an effective width that reaches all the way out to the same as your trip width. Typically, your effective width is going to fall a
No.
little bit less. And the reason you're able to stretch out that beam spacing is for two reasons. Number one, because it's a composite slab that has a lot more capacity. And then number two, because of the composite action you're getting from the slab on top of the beam via your stud shear flow. All right. Circling back real quick, Mac, to that pre-composite dead load. For pre-composite loads, we used 20 dead load and 20 live load. Know that the 20 live load is construction loading. What is included in the 20 dead load that will be removed prior to curing? Mainly just showcasing that that's a thing you can do. You could envision situations where that's true. I mean, let's say you're pouring concrete and it's 18 degrees outside, but somebody specified that you have to wet cure the slab. You could end up with a situation where you've got wet burlap and then, 12 pounds a square foot of insulated blankets on top, and the engineer wants to consider that dead load instead of construction live load, you've got the option to stratify that in your calculations and say, some of this is dead load, some is live load. It gets factored accordingly, but it all gets removed when you cure. Basically, just showing that you have the granularity to do that in your
Yeah, exactly.
calculation
This is
if
just
you need to.
showcasing that you can do this. This is just showcasing that
Exactly.
you can do that. If you don't want to do it, if you don't think that if you don't have an application for it, then that's a zero.
Yep. Is it not more cost effective to provide a temporary support at midspan? Again, that's more of a project specific experiential and judgment thing. We do provide the option for you to say that it's shored instead of unshored. Um, in the ENERCALC module, I believe that setting makes it completely shored, not a discrete mid-span shore. We're not doing any kind of a multi-span analysis to go, oh, now you're short at mid-span. Your beam now becomes two-span continuous during the wet, uncured condition. We're not doing that kind of analysis.
Yeah, once you do short, it stops looking at the pre-composite state. It assumes that it's sufficiently short, and that's the shoring engineer's problem now. It's not part of this.
Right. Now, if you needed to or wanted to, you certainly could go over to the ENERCALC steel beam module and
Exactly.
take that same beam, model it at the entire length, and then divide that span and get a two-span continuous design. You could do your own pre-composite check to evaluate for yourself whether it would be okay as a mid-span only shored condition. This module is doing continuously shored. Good question. Next question, is the software able to calculate based on SI units other than imperial units? At this time, ENERCALC is only working off of US imperial units and United States design codes. Next question, can I use angle pieces instead of rivets? I assume that that's referring to the headed studs that actually perform the composite transfer between the slab and the top of the steel beam. So the answer to that would be no in the ENERCALC module because we are going directly from the AISC steel composite design process, which is using those standardized headed stud anchors with standard geometries and standard strengths that are specified by AISC. I'm actually not familiar with using chunks of angle versus headed stud anchors. I don't think that it's considered by the American Institute of Steel Construction. All right. Next question. Is the allowable capacity of welded studs relevant only to the lateral seismic loads? And why design included a minimum number of welded studs? So the welded studs are, if you dig down into the theory of how steel composite works, the reason we call it composite is because you are building a combined behavior where when you think of a beam, let's say a simple span beam, for example, in flexure, when you have positive moment on that beam, the top flange of that beam undergoes compression, the bottom flange of that beam undergoes tension. And so the concept behind steel composite design is that rather than using only the top flange of the steel beam, steel flange and tension, or excuse me, steel flange and compression, we're using the combined behavior of some upper portion of the steel beam plus the concrete slab to provide compression capacity. So when you develop that tension compression moment couple in the transform section, you get a greater overall flexural capacity for the beam than if you were using only the bare steel beam. So when we talk about headed studs and transferring forces, when I say shear flow, that refers to the the actual transfer of forces between the steel and the concrete that gives you that combined composite behavior that lets the steel plus concrete be stronger than just the steel beam in traditional positive moment flexure. So we're not talking about lateral loads in a structure. We're talking about allowing load to pass between the slab and the beam in order to get a combined behavior that's stronger than the bare steel by itself. Hopefully that makes sense. Mac, feel free to jump in if you want to add something to that.
No, you've absolutely got it right.
Next question. How about restrained versus non-restrained diaphragm? Is there a difference in the design program? So the steel composite module that we looked at today doesn't really overlap or interact in any way with the concept of lateral design for a structure. So again, we're not using those headed studs to talk about diaphragm force transfer. We're not looking at this composite beam like it's a collector with axial force that needs to drag into the slab. We are only looking at the AISC dictated behavior to achieve composite flexure, composite bending capacity to carry gravity loads. Great questions. A lot of great discussion today. Believe it or not, Mac, we have wrapped up all of our questions there. And thank you
Fantastic.
guys for all the great discussion. That was really fantastic. Um, do you want to go ahead and close us out with a teaser for next month? We had one final question. Any considerations to cover British, South African, and Indian standards? We always have our ear to the ground to see what the demand is. So, the engineering team does track the demand for other design codes. Thanks for asking. Go ahead, Mac.
Yeah, next month's session is going to be on September 9th, and we will be covering the masonry beam module.
Fantastic. All right. Well, thank you guys for sticking with us. That was a half hour over the hour, but we love all the great discussion. We always look forward to you guys coming with all your great questions. As always, thanks everybody for making the time to be with us today. We will look forward to seeing you guys next month on September 9th. So bring your questions and we'll see you guys then.